Are graded is since the answers are in the book, I just look to see if you attempted the problem. If you made an effort at solving the problem, then you'll get full credit for that. If you leave it blank or there's minimal work there, then I won't give you credit. Now, how much credit is each question worth? Well, it varies. I mean, if there are only 10 problems in a 10-point assignment, then each question is worth 1 point. If there are 20 questions, 10-point assignment, then each question is worth a half a point. And so I take the number of questions in a particular assignment and then just divide by, or actually take the number that you did divided by the number that was assigned, and then take that out of 10 points. So it's actually worth a lot. I mean, this 3 chapters worth of homework, chapters 2, 3, and 4, so that's 30 points. I mean, the whole test was worth 100 points, so it's a big percentage of your points. And so if you didn't complete this, or if you didn't do the homework, you still have a chance. I'm not going to take a late penalty on the first set of homework here, but after this, then there's a significant late penalty. I need to see what you did for homework by the day of the exam. Okay. So are there any questions about the homework? We're starting a new chapter today, chapter 6, which is chemical nomenclature. Excuse me, so it's just naming. Elements and compounds. So when we have these formulas, we're looking at composition. So let's take a look back at composition. There are different ways to express composition. If we're looking at, excuse me, if we're looking at mixtures, then we're looking at mixtures. Would you say that actually, what would you say is the easiest way to represent the composition of a mixture? Probably the easiest way of representing the composition of a mixture is by percentage. And we have different percentages. For example, percent by mass is often used. We saw this before, like 7% chlorine in the chlorinating solution. 7% chlorine in the chlorinating solution means what? Yeah, 7 grams of chlorine over, 100 grams total. And so percent by mass is common. 7% chlorine in that chlorinating solution. Fertilizer, your fertilizer might contain 25% nitrogen, et cetera, et cetera. The mass, we can use any units. So for example, what if you use pounds instead? Would it change? So let's say I wanted to express 7% chlorine by mass. Well, it would be 7 pounds of chlorine for every 100 pounds of chlorinating solution. And so the units, we can use whatever units we want, pounds, ounces, anything. But we have to include the unit. You can't just say 7 gram or 7 over 100 because there's got to be a unit associated with that. And so percent by mass is common. So for example, water. Water, what's the percent by mass? Actually, is water a mixture? No, we're talking about mixtures. Water is what we call a compound. What about, are we mixtures? Is the human body made up of a mixture, or is it a substance? It's a mixture. And so if we're looking at, let's say, a complex mixture, maybe the easiest is a percentage. So let's take a look. You know what the human body is made up of? What the composition of the human body is? Nitrogen, oxygen, what else? Let me back up here. What else is it? Here. And so this is the percent by mass composition of the human body. Let's take a And so looks like oxygen. Oxygen is the largest percentage, with 65%. And so that means we have, 65 grams of oxygen for every, 100 grams of body. So, or for every 100 kilograms, we have 65 kilograms. Whatever unit you want to put in there, whatever makes sense. So, the percentage by mass. And then after oxygen, we have carbon, 18.5% by mass, hydrogen, nitrogen, calcium, phosphorus, potassium, sulfur. That's percent by mass. Sometimes we'll have a percent by volume. Percent by volume wouldn't be very convenient for the body, but maybe for alcohol solutions, it might be pretty convenient. So, for example, 90% alcohol, would be 90. Now we add units. Does it matter what units we put in there? No, as long as they're volume. And so it could be 90 gallons of alcohol for every 100 gallons total. Maybe it's 50% alcohol. It could be 50 milliliters of alcohol for every 100 milliliters total. And so we have percent by mass, we have percent by volume. Sometimes to differentiate these, we use this symbol, M over M, or W over W. M over M just means mass of component A, this might be chlorine, mass of component. And so mass of chlorine over total mass would be the mass of the mixture, however many components we have. So that would be an M over M percentage. And then we have a V over V. V over V. Percent by volume wouldn't be very useful for the human body. But we could have something else. We could have a percent by atom, which is also called a mole percent. We'll talk about moles later. Percent by atom. And so if we're looking at a percent by atom, the atoms weigh different amounts. So for example, oxygen weighs a different amount than carbon. Carbon weighs around 12 U, oxygen weighs around 16 U, hydrogen weighs around 1 U per atom. And so if we look at the atom distribution, it's going to be different, and so sometimes we'll just write percent MOL to indicate it's what we call a mole or atom percent. What atoms make up the human body? I know oxygen's the heaviest, right? But are oxygen atoms also the most abundant atoms in the human body? If you were to look at the atoms, not the weight or the mass, would the distribution look the same? Oxygen, carbon, hydrogen, nitrogen, calcium. What do you think? And the answer is, well, maybe not. I don't know if we expect it. And it turns out it's not. Do you know what the most abundant atom is in the human body? The most abundant, well, how many atoms are there in the human body? Do you know how many atoms? Approximately 7 times 10 to the 27 atoms are in the human body. So how many atoms are in the human body? 7 times 10 to the 27. 70 kilograms. And so if we look at the distribution of that, then looking at the atoms themselves, it looks like the hydrogen atom is the most abundant atom. Kind of makes sense because the body is made up of a large amount of water, which is H2O. So hydrogen. But the hydrogen doesn't only occur in water. The hydrogen also occurs in the proteins and fats, etc., that make up your body. We have oxygen, which occurs in water plus other stuff. And then it looks like, beyond that, it looks like probably the most abundant atom is carbon. carbon atoms. Very good. And carbon atoms make up most of the proteins, fats, carbohydrates. Then nitrogen, calcium, phosphorus, sulfur. And so this is an atom breakdown. This is going to give you atom or mole percentage. We have to take this number of hydrogen atoms, 4.22 times 10 to the 27, divided by the total number of atoms, 7 times 10 to the 27, times 100. So it's about 4 out of 7. 4 out of 7 would be about what? 40%? Roughly? Under 40%? Of the atoms. Whereas hydrogen atoms don't weigh that much. So when we look at the mass percentage of hydrogen is a lot lower. But anyway, when we look at composition in different ways, you know, it's helpful to see. Sometimes we'll do hybrids, especially for mixtures. You might do something like this. 0.9% M over V NaCl. And so this is an example of a hybrid one. So what does that say to you? How would you express this in units?
Density.
It's not density, actually, because it's not, what I write up here on the top is not the grams of everything, it's only the grams of a specific component. What component is it? Mixtures have multi-components to them, that is, multiple constituents that make up the mixture. And here we're only looking at one. Which one component of this mixture are we looking at? Well, this one would be 0.9. It's an M. What does M represent? Mass. So 0.9. Now over V, what does V represent? Volume. And so it turns out this is 0.9 grams over 100 milliliters. And so this would be 0.9 grams of what component? Well, it'd be pure sodium chloride, which is not a mixture. In this mixture, what is this mixture? It's 100 milliliters of what we call saline. Well, mixtures are not fixed composition, right? If you have a salt solution, the salt solution can be any concentration you want, you know, within certain limits. But this mixture is important. Have you heard of this one before? 0.9% MV. Well, this particular mixture. Let's see. Did I close that? I did. I gotta bring it up again. So close up window 0.9%. This is an important mixture. You can find this mixture. Let's shop for it. You can find it from a lot of different sources. Here. You see it? 0.9% sodium chloride. Let's take a look. These other 0.9% sodium chloride. And 0.9. I need to see where I saw it earlier. Okay, I need to see. Sorry. It was labeled. so if you look at this, this is actually a little bit more precise here. This is 0.90%. It's not exact. Depends on how precisely we make it. But 0.90% WV. What is WV? WV. Weight. You know, chemists use it interchangeably. Weight and mass. WV. So we could just as easily write this a WW%. We take it as the same thing. You know, weight percent. But the reason why this mixture is particularly important, and the reason why this concentration is particularly important, is because this is excuse me, what they use for intravenous saline. And that concentration is important because it closely approximates blood, the concentration of blood, called isotonic, for intravenous trips. And so here's a mixture that's pretty important, and you can buy, you can buy it from a lot of different sources. Much. All right, so those are mixtures, and mixtures we typically use that. And mixtures have variable concentrations. Since they have variable concentration, then this is probably the best or the easiest. And sometimes the concentration's low. If the concentration's low, then we might not use percent. Instead, we might use what? If the mixture has a very low concentration of a particular component, we might not use percent. We might use instead parts per million. But parts per million, is it the same thing? Yeah or no? Totally different. It's the same thing. It's just component A, mass of component. Rather than out of 100, it's going to be out of 1,000,000 or 1,000,000,000 or whatever. Okay, the next thing is, well, mixtures have variable composition, and we want to know the composition, of course. Well, what about compounds? The compounds actually, we should say substances. The difference between a substance and a mixture is substances have fixed composition. The composition doesn't change. Well, if it's a fixed composition, should we use percentage? Yeah, sure, we can use percentage as well, but we have other options too. And so we have compounds and elements. And so what's the composition of diamond? The composition of diamond is 100% carbon. And so we could use percentages, no problem. And so if we do percent by mass, or MM%, or WW%, let's look at water. Do you know what the percent composition of water is in terms of mass? We can find it if you want to look it up. On Wikipedia, they have the percent composition of water. Somewhere in here. But if not, we could figure it out. We can calculate it. So what is the percent? Well, it turns out if we sit down and figure it out, it turns out that the percent composition by mass is 89% oxygen and 11% hydrogen. And so water consists of 89% oxygen, 11% hydrogen by mass. Would we do a volume percent? Would it make sense to do a volume percent? Now you could, depends on how big a hydrogen atom is. It'd be kind of a tricky problem because you have to figure out the total volume of this and then figure out what percentage of the volume is bread and what percentage is the white. Not that easy to do. So it'd probably be easy to do it by percent by atom. So if we look at an atom or mole percent, what is the atom or mole percent? Well, here, if I look at water, water has how many hydrogens? 2 atoms of hydrogen for every 1 atom of oxygen. So it's a total of 3. So 2/3 of the atoms are hydrogen. Well, convert 2/3 into a percentage, we just multiply by 100%. So 2/3 times 100% gives us 67%. I'm rounding here. 67% hydrogen and 33% oxygen. And so in terms of percentage composition, these are both for water. So if we look at the percent by mass, it's telling me that water consists mostly of oxygen. If we look at it based on atoms, then it tells me that water consists mostly of hydrogen atoms. And we want to know both because both tell us a little different information. It's like the composition of the human body. The composition of the human body in terms of mass versus the composition of the human body in terms of atoms. It gives us different information. It gives us different insight into it. And so we want to know both. And so what we can do is we can express the composition as percentages, right? But we have other options as well. The other options is we can express the composition in terms of a formula. A formula is like an atom ratio. We have 2 types of formulas that we typically deal with. One type of formula is called the empirical formula. Empirical formula. The empirical formula is the simplest whole number ratio. Simplest whole number ratio of atoms. The simplest whole number ratio of atoms for water is H2O. It's a 2-to-1 ratio. Two hydrogens for every oxygen. And then we have another formula called the molecular formula. The molecular formula is the ratio of atoms in a molecule. Or just number of atoms, ratio of atoms in a molecule. And so for water, it'd be the same. And so water, the empirical formula and the molecular formula are the same thing. But for hydrogen peroxide, it's different. If we look at the empirical formula for hydrogen peroxide, it would be HO. But if I look at a single molecule of hydrogen peroxide, it's not HO. Let's take a look at a molecule of hydrogen peroxide. And this would be a molecule of hydrogen peroxide here. A molecule of hydrogen peroxide consists of 2 hydrogens and 2 oxygens here, all bonded or linked together. So the molecular formula here would be H2O2, would be hydrogen peroxide. And so sometimes the empirical and the molecular are the same. All right, so what would the molecular formula for salt be, table salt, sodium chloride? What would the molecular formula for sodium chloride be? Okay, NaCl, NaCl2, Na2Cl2. Yeah, sodium chloride doesn't form molecules, so we can't. So NaCl, since it doesn't form molecules, we would not have a molecular formula for sodium chloride. In fact, sodium chloride can only be represented as empirical formula, NaCl. Let's see. And the reason is because of the structure. NaCl, when we look at the structure of it, it doesn't form discrete individual molecules, and instead it forms what? Lattice. Good. What kind of lattice? We discussed some different types of lattices, which we'll talk about later, but does anybody recall what type of lattice NaCl is? It's an ionic lattice. Okay. What other types of lattices did we encounter? We encountered ionic lattices, covalent lattices. Give me an example of a covalent lattice. Quartz is an example of a covalent lattice. Diamond is an example of a covalent lattice. Graphite is an example of a covalent lattice. And then there's one other type of lattice that we have, metallic lattice. And so for all the lattice structures, you can only use the empirical formula. There's no such thing as a molecular formula for lattice. And that's because they don't form discrete molecules. I mean, there are small clusters, which you might call molecules. Like, so for example, if you vaporize copper, you might form little clusters of copper. And these little clusters of copper, you might think, oh, those are little molecules of copper. But the difference is that you can have different size clusters. You know, there's no beginning, no end to the cluster size, right? Whereas in a discrete molecule, there is a beginning and there's an end. It's a fixed entity like hydrogen peroxide. You aren't going to have, you aren't going to have clusters of hydrogen peroxide that are all bonded together. There are water clusters, but they aren't all bonded together. And so some things will only have empirical, some things will have both empirical and molecular. Which one is more informative? Well, which one's more informative? If it's a lattice structure, then yeah, empirical is going to be the most informative. However, if it's a molecular structure, then we want to know the molecular formula, because we want to know what the discrete molecular unit consists of. Here, if we're looking at the empirical formula for hydrogen peroxide, it doesn't give us that much information because a 1-to-1 ratio could be 2-to-2, or it could be 3-to-3, or 4-to-4, 5-to-5. Well, it turns out it's a 2-to-2 ratio. Could have been higher, we just don't know. And so we've got to be aware of that. And so when we're dealing with formulas, we need to know, is it an empirical formula or is it a molecular formula? But when they label chemical bottles, they don't want to go through that hassle. When you label a chemical bottle, you could label it the empirical formula, or you could label it molecular formula, or you could just call it the formula. Or instead, the formula unit. And so let's take a look at one more. We'll do this. And so we have something called the formula unit. The formula unit is just a general term for the formula. And so when you see formula unit, we can't tell if it's molecular or empirical. And so it's a general use term. In order to determine if it's empirical or if it's molecular, we need a little bit more information. We need to know. So just a general use term for both. And so here's water. That would be a molecular, empirical, both. Both. Here's sodium chloride, molecular, empirical, both? Empirical only. Helium. Helium, when we think about helium, what's the structure of helium? Helium is a gas. Helium gas consists of helium molecules, helium lattice, helium atoms. Helium atoms, just individual atoms going around. They're not bonded together. However, lithium. Lithium is a metal. Lithium would metals form a metal molecule or individual atoms. What do metals form? Metals form a take a look. lithium forms. These are some lithium compounds. This is lithium here. Although you can't really see it because they spread out all the atoms. This is the lithium lattice, and it's all compressed together, but they just spread everything out so you can see. Otherwise, you just see the face of it. So this is the lithium metal lattice. Do you see an individual or discrete molecule? No. What we see is we just see a whole bunch of atoms in there. And so the easiest is to use the what formula? The easiest thing is to call this by its empirical, molecular, empirical. And the empirical formula for this is the simplest ratio. The simplest ratio is just one lithium. And so this would just be Li. That would be the same thing as the formula unit for lithium. So lithium crystal structure. So was it. There's some others. These are all examples of lattices where there are. This is the lithium chloride lattice here. This is lithium fluoride lattice, lithium hydride lattice, a whole bunch of different lattices. This was quartz. This is a quartz lattice, beta quartz, and this just keeps going. You know, in 3 dimensions, there's no real beginning, no real end. It doesn't form discrete molecules here. Quartz. Quartz crystal. Here you can see a much bigger portion of that just extending out. So these are the lattice structures here. All right, let's go back to those slides. Here. And so this would be an example of the empirical formula here. But we have some elements that exist as 2-atom molecules. I already asked you to memorize these. See it on the next slide. What are they? Hydrogen. And so when somebody's talking about hydrogen, hydrogen gas, they're talking about H2, these 2 atoms. And the 2 atoms of hydrogen are bound together chemically. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These are what we call the diatomic elements. Most of the other elements we represent as empirical, that is just only the. So for example, under oxygen is sulfur, in this blue square. Sulfur is just usually represented by S. Most of the others. However, you know, it's a little bit more complicated because these are the diatomics. Some of these other elements form more complex molecules, and others don't form molecules. So let's take a look at 2 additional examples here. This is yellow sulfur. This is what it looks like. It's normally powdered, but it could also be crystalline. Actually, I'm going to show this. If you look at the formula for yellow sulfur, do you see what the formula is? It's S8. And so would that be an empirical? No, empirical would just be S. This is what we call the molecular formula for sulfur. It's a molecular formula for sulfur because sulfur forms discrete molecules. What do these molecules look like? The molecules look like this. Actually, this is not it. Where did I put that? Okay, what do the molecules look like? The molecules look like this. There's 8 sulfur atoms bonded in a ring. They call it like a crown. And And so one discrete, and they pack together like this, even though you can't really see it. But those are a whole bunch of those 8-membered rings packed together in a solid. Remember the solids are touching. This packs together quite efficiently. Leads to crystalline sulfur. It's S8. One more. This is different. This is a different structure entirely. This one is called yellow sulfur here. This one is called white sulfur, and it has a white color. Yellow sulfur and white sulfur have quite a bit different properties, just like diamond and graphite have different properties based on their structure. White sulfur is like a rubber. It stretches, doesn't melt very easily. But it doesn't occur as discrete molecular units because this has no real fixed beginning, no real fixed end. This chain of sulfurs can continue on for long distances. And so the best thing to represent white sulfur is not the molecular formula. The best way of representing white sulfur is, since there's not an individual, some of these chains are short, some of these chains are long. The best way to represent white sulfur is by using its empirical formula, which is what? What's the empirical formula for white sulfur? S. And so this would be S8, yellow sulfur. White sulfur is just S. You know what these are called? These are called allotropes of sulfur. Allotropes. Allotropes are the same element, with a different structure. Another example of an allotrope or a set of allotropes would be diamond and graphite. Diamond and graphite are both pure carbon, 100% carbon, but they have different structures. And therefore, they're allotropes. Not to be confused with isotopes. Isotopes are a little different. And so, what are these? So this is white or yellow phosphorus here. This is red phosphorus. This is 100% phosphorus. This is 100% phosphorus. So both of these are pure phosphorus. But their properties are quite a bit different. Their properties are quite a bit different, not because of the composition, because they're composed of this exact same thing, 100% phosphorus. Their properties are different because of the structure. And so let's see, red phosphorus is odorless. Red phosphorus we use in matches. White phosphorus you don't want to use in matches because actually white phosphorus will start to glow, you know, and under normal conditions. It starts to glow because it starts burning. It's dangerous stuff. Red phosphorus is non-poisonous. White phosphorus is poisonous. White phosphorus is garlic-like odor. Red phosphorus is odorless. Why are the properties so different? Well, it has to be related to the structures. White phosphorus is highly reactive. Red phosphorus is less reactive. White phosphorus is waxy, easy to cut. Red phosphorus is hard, not easy to cut, and it's crystalline. Actually, both of these are crystalline. White phosphorus shows phosphorescence. It starts to glow. It'll glow in the dark. Red does not. The ignition temperatures are quite different. The ignition temperature, both of these burn. And to burn white phosphorus, you need 303 Kelvin. What is room temperature? 298. What this ignition temperature means is you just have to heat it there and then it'll just ignite. No match needed. And so we just have to heat this just above room temperature and it'll go up. Whereas red phosphorus, you need a much higher temperature, 543 Kelvin to ignite it. You don't need flames, you just need heat, etc. So these are some of the properties. Well, let's take a look at the structural differences between red phosphorus and white phosphorus. When something's soft, waxy, solid, do you expect that to be a lattice like quartz, or do you expect that to be molecular like ice? It's actually white phosphorus is going to be molecular. And so white phosphorus consists of these molecules. What's the formula for this? I'll tell you the empirical formula. The empirical formula for white phosphorus is P. What's the molecular formula for white phosphorus? P4. And so white phosphorus is P4. Red phosphorus, well, I'll tell you the empirical formula for red phosphorus is the same. The empirical formula is P. What's the molecular formula for red phosphorus? The molecular formula for red phosphorus. Do you see a discrete beginning and end to the molecule? Does the molecule begin here and end there? Then we just count the atoms. No, it doesn't. This doesn't have, in fact, this is what we call a polymeric structure. This is what we call a monomer here, and these monomers are connected together to form a polymer, a longer chain. It's a polymeric structure. If we have a structure like that, there's no real individual size. Some of these chains are long, some of them are short. We see all sizes in between. And so the best representation for, this is kind of a lattice, but it's a unidimensional, one-dimensional lattice, just on the x-axis. Do you see that? And so when we look at red phosphorus, probably best not to say molecular, since it's a lattice structure. The best is to say empirical, right? And so we would use the empirical formula for red phosphorus. It's just P. And so going back to this, we would call this P4. This is just P. All right, but that's digging into it deeper than we need to. So you don't have to memorize white phosphorus. You don't have to memorize white phosphorus is P4, red phosphorus is P. You don't have to memorize yellow sulfur is S8, and white sulfur is S structures. But what you should know is, like, most of these we'll just represent using the empirical formula, and that's adequate for us. But a lot of these elements, they form different types of structures, and so it might not always be correct. All right, so let's go ahead and write the formulas for some of these. For example, chlorine. Chlorine consists of 100% chlorine. Now, how should we represent that? Yeah, chlorine is a diatomic. It's a molecular element, and so it's Cl2. You should just memorize it, Cl2. It's not to say Cl can't exist. Cl can exist, but it's highly unstable, much more unstable than chlorine. Argon. Argon, is that molecular or is that lattice? Molecular or lattice? Or am I missing one? Molecular or lattice? Actually, it's just atom. It's neither. Argon's just single atoms in gas phase. Ar. For argon. Bromine, atoms, molecules, or lattice? Molecules. And the formula? Br2. And krypton, atoms, lattice, or molecules? Atoms. Krypton would be atoms. That would just be Kr. So let's just do a quick check. Chlorine, Cl2. Argon, Ar. So chlorine consists of molecules of Cl2. Argon consists of atoms of Ar in the gas phase. Bromine consists of molecules of Br2. And krypton consists of atoms of Kr. So when we look at the periodic table like this, the metals here all form metallic lattices. Since they all form metallic lattices, there's no distinct beginning or end to the crystal. You can have big crystals, you can have small crystals. And therefore, we're going to represent all the metals using its empirical formula. And so for copper, it would just be Cu. For lead, so around over here, it would just be Pb. Now the nonmetals, some of these form molecules. The ones that form molecules for the nonmetals are going to be hydrogen, nitrogen, oxygen, chlorine, the 7 that you're supposed to memorize. And then a few others. A few others form molecules. And then we have the noble gases. The noble gases just form atoms. And everything else we're just going to represent using its empirical formula. Okay, there's a transition in going. You know, the way the periodic table is arranged is based on properties. And the periodic table came about even before the theory of chemistry was developed. And it's just based on families, which are these columns. And members of the family behave similarly chemically, and they have progressive physical properties as well. That is, they change in a progressive manner. And then we have these things called periods, which are these rows. And the periods, the properties change gradually. And so we gradually go from metal, and it becomes less and less metal-like, and more non-metal-like. And then there's this transition region in green, and then we go non-metal. This green region, these elements have properties of both metals and non-metals. Those are called the metalloids or the semi-metals. So the first thing we're going to encounter here, nomenclature, and these are rules. We're going to learn a whole bunch of rules for naming compounds, elements. This is for the binary molecular compound. The binary, do you know what binary means? In this case, 2 is correct. So this is going to be 2 elements. All right, molecular. Well, how do we know if it's going to be a molecular structure or a lattice structure or single atoms? How do you know? Well, one way you can know is by memorizing it. So for example, quartz. You memorize quartz is a, what we call a covalent lattice. We memorize that sodium chloride is a ionic lattice, that kind of thing. So we can memorize them individually, but is there any pattern that we see? And the pattern that we see is this, that most molecular compounds, binary molecular compounds, consist of nonmetals. And so 2 nonmetals. When we have 2 nonmetals, like carbon and oxygen, then they tend to form molecules, like carbon dioxide. Carbon dioxide, is it a lattice structure or a molecular structure? Or yeah, it's molecular. Nitrogen dioxide, molecular. And so we got 2 nonmetals, but let's say typically, because there are violations to this. There are ones that aren't necessarily. So for example here, NH4 with a plus here. Is that binary? Well, one thing we might say is this is not binary because this has 5 atoms. 1 nitrogen atom and 4 hydrogens. And therefore, can I exclude that from being binary? Or is this binary also? It turns out this is binary, because binary doesn't refer to how many atoms you have. Binary just means you have 2 elements. So this is binary. Check for binary. Then, are we dealing with nonmetals? Nitrogen is a metal or non-metal? Non-metal. Hydrogen is a non-metal. And so we would expect it to be, non-metals. Check. Good. And so is this a binary molecular compound? And it's not. The reason it's not is because of this. This is not a compound. This is something that we call an ion, which we'll talk about later. An ion consists of an imbalance of protons and neutrons. So somehow a electron was lost, and so one of the protons in the nucleus is not charged balanced. And so it's an ion, therefore not a molecular compound. And therefore we can't use these rules for this. This set of rules is just for binary molecular compounds. What if we had something like this? HNO2. Is that a binary molecular compound? The ion is charged, sorry. Charged. Well, it's not an ion. It doesn't have a charge. It consists of all nonmetals. Well, it consists of all nonmetals. This consists of molecules. Therefore, this is a molecular compound. Yes. It's a molecular compound. But there's a problem with this molecular compound. What is the problem with this molecular compound? It's not binary. This molecular compound is what? Yeah, this is trinary, right? I guess trinary would come after bi, right? So trinary. And therefore, it doesn't work. It doesn't work. And so we got to think. How about this one? H2O. Is that a binary molecular compound? Yeah. Yeah, this is a binary molecular compound. Even though we have a total of 3 atoms, we only have 2 elements making it up. And so for H2O, well, we already know the name of this. What is the name of this? The name of this is water. Water, we call its common name. Common name. And we memorize it. Common name. The common name is its traditional name based on historical reasons. That's our common or traditional name. But if we followed these rules, we'd come up with a different name for water. Water would be called dihydrogen monoxide. Oh, you heard of dihydrogen monoxide before? Dihydrogen monoxide. Dihydrogen monoxide is also called a DHMO. DHMO. And DHMO you might have heard of. Because of the band, the DHMO band. That's a petition. I don't know if this is some kind of ongoing joke, but there was, I think, a city in Northern California wrote a resolution, and then Aliso Viejo almost banned it. Came close to banning DHMO. Yeah, they almost banned it. It's embarrassing, said City Manager David J. Norman. We had a paralegal who did bad research. So. But it's an odorless, tasteless chemical that can be deadly if accidentally inhaled. All right. So this other one, though, I have experience with the traditional or common name for NH3 is ammonia. And I know about ammonia. I don't know about its other name. So when I was in it, I needed to order some ammonia, so I went to a chemical catalog, and then I was surprised I couldn't find it. I was looking all over in this chemical. It was from a big manufacturer, and I couldn't find it because you know what they called it? They didn't call it ammonia. They called it nitrogen trihydride. So I wasted a lot of time looking for it, but I found it pretty easily. Nitrogen trihydride is what we call it. And so when we look at the name here, we have these prefixes. The prefixes just tell us the number. So di is for 2, mono is for 1. And then we have an ending on the end here, I. Notice that. And so here, CO, what's that one? Carbon monoxide. This is binary molecular. CO2, carbon dioxide. And so we just changed the ending. So the nomenclature rules, so we can get more practice to figure it out. But we only changed the ending for the second element, not the first element. So the second element is the IE. So what are the prefixes that we're going to encounter? Let's take a look at the prefixes that you should memorize. So mono, di, and 3 is tri, 4, tetra, penta, hexa, hepta, octa, nona, and deca. Some of these aren't that common, like mono, di, tri, tetra. Those are very common. Penta. Nona is pretty rare. Don't really use it that much. Don't see that many compounds with nona. And so let's try some of these here. Tell me what the formula is for dinitrogen pentasulfide. Dinitrogen pentasulfide. That would be N2S5. Good. Dinitrogen. Okay, this is a funny thing. What happened to the A? If we look at this, this is pentasulfide. This should be pentaoxide. But you know, it gets mixed up when you have these double vowels. So rather than calling it pentaoxide, they drop the A and call it pentoxide because it just flows easier. And so dinitrogen pentoxide would be N2O5. Dinitrogen pentoxide. And so oxygen, we have to change it. You know, nitrogen we leave alone to say 2 nitrogens, but the oxygen we have to end in I. And so we have different choices. We could call it oxygenide. Does oxygenide sound good to you? Carbon oxygenide or carbon dioxygenide. No, it doesn't quite flow, so we keep dropping syllables until it flows. A little easier. And so dinitrogen pentoxide. How about the next one? The next one is going to be called tetra for 4, io, di. Now the first one read the ending. So this would be tetraiodine or iodine. tetraiodine. The second element, we're going to change the ending. So I said nona is not that common, but now we have a nona here. It's probably the one and only nona you're going to see. But what would we call it? Would we call it nona oxide or nonoxide? Yeah, this one's going to be called nonoxide. So tetraiodine, nonoxide. Okay, the last one. This is going to be, should we say monophosphorus or just phosphorus? Monophosphorus or just phosphorus? Well, we have to think, is it monocarbon monoxide or is it carbon monoxide? It's carbon. So just based on experience with these, it's probably just phosphorus, not monophosphorus. So we'll just call it phosphorus. What's phi? Penta. And then rather than fluorine, we're going to call it fluoride. And now note the spelling on fluoride. It's FLU, not FLO. So here, phosphorus pentafluoride. All right, let's take a break. Oh, did we already take a break? No, let's take a break now. This clock is screwing me up. It's already 6. Thinking. Okay.